Yeah, we can. Once we have like the layer, we're gonna save the layer. So that way we can keep doing that part. So that way it's just make that all researchable, but then
Huge closet. Yeah, there's so much space inside. There's a kitchen area next to it. Not so love them dearly. I love them a lot. I haven't seen them since it's Sam's dog. So yeah, that was the right. Yeah. Sitting to us. All of our social clubs. They're fortunate. They didn't see everyone for how long. I know. Those days. I know. It is not every week. All those things.
Okay, sorry for the late start, but we're gonna go into satellite imagery some more and using Google Earth Engine. And today we're gonna go into Python. What I'll do is go through this module and then go back, visit the Slack and talk a little bit more about the deep learning lab, because I know it's pretty confusing, truth be told. Just with how the layers kind of interact with each other and the shape of things. So last time we went over Google Earth Engine and using the JavaScript editor. So, and we could see how quickly we can actually grab these petabytes of data sets and then run machine learning and like the unsupervised clustering method, and then the supervised random forest method. And many of you were asking to do more in Python as to beef up your skill set there. So this is just a little exploration of using Google Earth Engine with Python and applying that same technique. And before we go into that lab, I realized like maybe I took for granted some of the stuff when I mentioned bands and then pixels. And so these are just going, have you guys gone over a lot of satellite imagery already? Yeah, okay. Well, then these are slides that are just like a big overview for Google Earth Engine. So it does talk a little bit more about some of the stuff under the hood. So yeah. And yeah, these are all the functions. And just the notion of different bands, and each pixel can have multiple bands, and I wasn't sure if that was clear. And the fact that, yeah, you can extract the pixels for these different geometries, which is kind of how some of this operation is happening. So yeah, there's a lot of stuff that's happening with tiling and pyramiding as you zoom in and out that it handles for you, because otherwise it becomes quite cumbersome with a lot of compute power to otherwise generate that stuff. So that's just very basic little background. But let's go ahead and get into using Google Earth Engine with Python. It's not that one. And sorry, let's see if this is updated yet. Okay, yeah, just updated. So you might have to refresh. And then let's make sure, yeah, and then Google Earth Engine 5B, okay. And then we're also going to introduce this other thing called a Colab notebook. So this is just a Google hosted Jupyter notebook, and they've got some other little special treats, like a nice table of contents, different themings. They automatically have different packages installed, and you have access to GPUs. And so far on Taylor, we only had a CPU. So when you started doing some of that classification, it really started to bog down with the convolutional neural nets and the image processing. The GPUs, it'll run a lot faster. So yeah, maybe next year we run this more with this Colab notebook. And to get started, what you want to do is visit this Colab notebook. So just by clicking the link, and so this is already pre-rendered. Oh, good, showed up like I was hoping. Okay. So now what you want to do though is before you start running it, so that you have the ability to save it and make changes yourself, let's go ahead and do this. So hopefully you have access there. And I say this also in just this first heading, so don't worry about getting lost here, but it's really just as simple as going File, Save a Copy in Drive. And then you'll get a few prompts. Like if I changed, let's see, if I changed into a different user, and now I go File, Save a Copy in Drive. It's creating a copy, and it'll say copy of. And if you look at locate in Drive, like where it shows up in your drive, in your Google Drive, it automatically creates a folder called Colab Notebooks. And so that's just where it's going to default put stuff. And you'll notice that it has the same file extension, IPython notebook, as a Jupyter notebook. So it's actually fully compatible with running in another Jupyter notebook environment like on Taylor. Yeah. So if we look at this a bit further, and remember this clustering exercise that we had here, where here's the JavaScript code editor code for it. And we have like sort of two things going on. One is loading the data and then actually running the clustering. And then secondly, we also have like a visualization side. And so the visualization side, it's starting with this map. So it's saying, okay, Earth Engine has a map object, and now we're going to set the center, add a layer, and then visualize this classified layer. And now things start to look a little different in Python. So in JavaScript, generally you're ending a line with a semicolon. But Python is also object-oriented. So you have an object.method or object.property pattern. So now if we go back here, you'll see that we have a clustering kind of. So this is without the visualization. And then secondly, we'll talk about actually making an interactive map, which there's some prep work to do, but eventually we do get to the point where we have an interactive map and we can zoom in and out and toggle some layers on and off. So if we just take it from the top, with this Google hosted Colab notebook environment, there's this Earth Engine or EE module already installed, already available. And so we can import that. And what you'll notice is when you actually hit play on this, so it's going to import this module. And then there's this authenticate step. And this is where you need to follow this link and then authorize Google Earth Engine to then use this stuff. And then you clip on that little clipboard, and this copies this authorization code. And then there's a little box here that you can then paste it. So this authentication step is a necessary like manual step to actually run this notebook. And then the third step in just getting this set up is just initializing Earth Engine. So this is sort of this is the Python precursor to actually doing anything with Earth Engine that you automatically is basically running on the already in the JavaScript. And then it's very similar from here on. So we have and we could actually just look at these even side by side so you can see the comparison. So if we look kind of compare, so in JavaScript, if we're setting a variable, we prefix it with var and then we set it equals to something. In Python, we can just set it equal to something directly. And so otherwise, it's the same. You actually can use a semicolon in Python also. And that was me forgetting that one. But the semicolon in Python allows you to then subsequently add another command. So that's still okay. And then some stuff like in JavaScript, it has this like curly brace, and this is how it defines a dictionary. That's actually the case also in Python to define a dictionary, which is a key equals value kind of concept. But in Python, this function actually just takes those arguments directly, meaning that there's an argument for region, scale, num pixels, and it reads that directly. And then this is basically, yeah, identical. And so is the next line to actually do the clustering on a given image. And then there's more help if under further resources, and actually I reference, let's see, here in this Python installation, there are these common syntax differences. So if we scroll down, you can see this table, and it's showing us, it's just kind of comparing how actually JavaScript looks pretty much like R in that to define a function, you have, it's very similar that you have the curly braces to describe the expressions between. And of course, with Python, you're indenting after a colon to then say that that's all the code associated with that function. Yeah, I mentioned the prefixing with var, but actually like dictionaries with a key and a value are kind of similar. So it's just a little syntactic difference, not too rough. And really the value of using Python is that you can do like much bigger jobs and batch run stuff, and automate things. And then you might have also other powerful like Python libraries that you want to use for other visualizations or analytics that you can then bring into use as well. Yeah. Okay, so then now we'll talk about just, okay, how do we look at it? And you can export thumbnail images directly with Python, but it's just a lot more fun to interactively like zoom in and out and pan around. So this is what's already also installed in this library. Folium is already installed in this Colab notebook environment. And Folium is just a library that wraps the leaflet JavaScript library, just like there's a leaflet R library that wraps those functions. And have you guys heard of HTML tools, the framework? Because that's so this is actually where a lot of there's a very similar concept in oh, this not HTML tools, HTML widgets, sorry. So this concept of basically taking a JavaScript library that is made for the web and to do interactive things, that's the programming side of your web browser that does all the interactive things, and then to basically create little R functions that can then generate that with very little code. So, you know, this is what you guys you've used the leaflet library, and then it can just make an interactive map, and that works in an R Markdown environment. And so this is basically the same idea, is Folium wraps that JavaScript library and then makes it available in this Jupyter Notebook environment. And actually, like, as far as I thought this was kind of interesting. So that, you know, the open source world is dependent on volunteers, and you go to this leaflet page, and now we see like, okay, so this thing was created 11 years ago. It's used the world over by a Ukrainian citizen, and he's no longer in Kiev because Russian bombs are falling. He's like, yeah, reality. Yeah. So anyway, that's, I found interesting. Yeah, so we are a global village, and we depend on each other and each other's well-being. So that's just a good reminder of that. Okay, so to use this back to the Folium stuff, normally Folium is used to just take more standard objects. There's a little bit of extra work to basically interface Earth Engine with Folium. And this I just copied and pasted from their documentation, but it also serves as a nice example of how a Python function looks. Have you guys created Python functions in other classes? Okay, cool. So we've got a def to define it, the function name, and then in parentheses, the arguments that are going to go in that it expects. If you put an equal sign after a given argument, then that means that you could assign a default value, and then we're indenting everything inside the definition of that function, and usually we're spitting out a result at the end. So this has a try except wrapping around it, which is just doing some error checking. But the idea, what I'm hoping that you guys can chew on, is just create a function using these chunks of code to then do the clustering, and for an arbitrary region, an arbitrary number of clusters, and a few other parameters to just visualize the output. And so this is just setting up the Folium map Also, there's a little bit here that says like, here are the base maps. This is also just a dictionary. So here's the key is the name of this, and then this is the parameters for the tile layer. So the way these like rasters or base maps basically come in is tiles. And sometimes when it's like slow to render, you'll see the little tiles are blanks as you might zoom in and out and pan around if you have a slow internet connection. And so it's only your client using JavaScript is just basically requesting to that tile server, okay, here's my zoom extent and the layer I want. Now send me the tile. So it's just visualizing just basically a bunch of images that it's sending back. And then if I change the zoom level, then it's going to be a different set of images, just specific to that extent. So it's only sending from the server to the client what it needs to give you this visual. And those are just the little parameters to specify, to basically apply attribution. And here's the URL for those tiles. So so this is just setting up the default layer, and we have a location, latitude and longitude. And it's really good to just know how to dive into the documentation of any of these functions. So we can go here, and here's the Google Earth Engine documentation about like, here's the JavaScript version that gets used to set the center. You can see that there's a longitude first and a latitude. And this is, sometimes these things are flipped, lat long versus long lat. And it's good to be able to dive into this documentation. And I might have even misconstrued this. But, and then this one, we have the documentation, and it's location, and this was latitude and longitude. So, yeah.
In our remote sensing class, we use something called GMAP or GE.
Ah, I was going to ask you guys.
I'm wondering.
Yes.
What's the difference, or like?
Thank you. Yeah. So I mentioned the GMAP. Where do I mention that? After all this extra definition. Yeah, so I have a link to it. And GMAP has a lot more functionality, and you wouldn't have to define this like that function that I just had. You could just do it. And it seems pretty great. The only reason that I didn't proceed with the GMAP is that it's not natively installed in this Colab environment. And when I did install it, it worked for the functions I used, but it also flagged that there's some version dependencies that were mismatched. And so it created a lot of like, there's a lot of red text and errors that I didn't want to like deal with. And so I'm glad you mentioned it. I was debating about going with it and just like, yeah, ignore the errors. But I thought it was also good as an introduction to the Colab environment, just to see what is kind of natively recommended and used. But you could absolutely use GMAP because there's a bunch of extra tools to like do histograms and work directly with Google Earth Engine and look at time series. And you can even, like, one of the nice things I saw was that you could set the center of an object. So right now we're defining a latitude longitude to center the zoom, and then the zoom starts. So that's the zoom level of like, I think 1 or 2 is global. And then as the number increases, the zoom, it becomes more fine. But if you like, the GMAP has you can set a, what is it, center object or something. Yeah. And you wouldn't have to figure out what the centroid is. So it has a lot of helper functions and adding legends. So it's a great thing to do. I'm glad that you got it last quarter in Smith's class. Yeah, cool. So that looks like a great library. I recommend it. But there was just some versioning incompatibilities that made me resist installing it. And to install any package, it is actually quite easy. So this is saying, the exclamation is shebang. It's like saying just run, not in the Python environment, but run in the like terminal environment. And pip is the Python, I don't know what it stands for. Used to be called the Python cheese shop because it was all these Monty Python references, but it goes to the central repository of where these modules, as they like to call them in Python, which is the same as a library in R, as where the modules are installed. So it just boom installs it. So we can actually run it, and you guys can just, I'll just show you what it looks like. Let's see if I just add code and then hit run on this. You'll see it goes and it fetches all the dependent modules, starts downloading. We'll come back to it in a sec. And then the other thing that previously you had in that in this guy was this random visualizer. So that, can anybody tell me what the random part is of that visualizer? Well, it's basically, how do we color the classes? So it's randomly assigning a color to the different values, unique values of the pixels in the image. So that is also one of these things that's available in the JavaScript side, but it wasn't clear to me how to use it on the Python side. So this also points to how with Python, you can kind of mix and match these other libraries fairly easily. Have you guys used Seaborn yet? Yeah, some? Okay, cool. So yeah, Seaborn is a great visualization library. It's kind of like the ggplot for Python, I'd say. And before that, there's Matplotlib that is like still around and is great, but Seaborn, they have some nice, they have some prettier defaults basically. But so this is, we're importing the library and giving it a little smaller name for lazy purposes, and then using this color palette function. And I just was Googling like, okay, how can I get a color palette? Because I don't have that random visualizer option, and ended up on this documentation here. And so from this, I could see, okay, I got that. I can generate this palette. So this is, and Seaborn is also natively available in this Colab environment. So this is showing the color palette. And so you can imagine that as your clusters would change, maybe that's a variable that I'm suggesting you use called K. And as K changes, then because we're using K means clustering, then you would expect to see a different number of colors here on the palette. So right now it's 15. And this is the part where, as data scientists, you want to be able to go from hard coding as a single operation to then generically making a function and then reusing it and retooling it time and again. And then there's this viz params. So this is just another argument when we actually go to add that classified layer. And so again, here we see the min is 0, the max. So this is saying what values do I stretch that color palette across, and this is where you could input the number of clusters like that K right there. And then we zoom into an area, we can add some pretty base maps. And here the main thing is adding our classified image results with this color palette applied, and then maybe some little name here. And again, that's a hard-coded 15, but we could construct a string you know, if I said k equals 3, and then I actually I'll just do this in a different cell. So I'll add a little. So I could just print and run this, and that doesn't work. Only concatenate strings. I'm pretty rusty on Python. Let's see, does this work? Yeah, sort of adds a space there. There's also this, let's see. I can do this sprintf thing. %s, and then is that right? Yeah. So this is saying, okay, actually this would be a k as a number, as a digit, so that would be a d. Have you guys done like concat? Have you constructed strings in Python already? Okay, cool. There's actually a whole bunch of ways to do this. Any other ways that come to mind? Okay, so yeah, you could do that for that little guy there, and then this adds these layer controls. So this is a layer control, and we can just display it. So I haven't run the previous stuff, so you just say runtime run all, and now it's going to ask me to authenticate again. And so this, these Colab notebooks, they're only alive for a certain amount of time based on, it's like from maybe an hour to a day. And then you would have to rerun. But yeah, so we get this map output for the region, and then I can, like the Gmap, you could actually set opacity and do a bunch of other kind of cool stuff. This one, I can just turn on and off the clusters, maybe see the different map base layers behind it, and turn off and on the region, and just zoom in and out. And this thing doesn't seem to really work. It just gets a little bit bigger, but it doesn't go full screen like I expected with this name. So yeah, so the task, I think, like just a good, you know, practice to using Python is, okay, so we're gonna do some machine learning. You guys already saw this in with JavaScript, and then try to create a function that uses these input arguments where you've got you have an input image, you have a region that was previously defined as a rectangle, a number of clusters, the longitude, the center, latitude, the center, the zoom level, and then use the cells above. So these are just links to those code chunks, which I got from, apparently this is a thing you can do, where I can just go to a given code chunk. Is this true in Jupyter Notebook too? Where I can just click on this link. So now I can copy that link, and it should go back to that code chunk. But I don't know, as things change, I'm kind of curious. So now it's a new window, and yeah. Oh man, that changed, of course, because I added this little pip. I think pip messed it up, but here is that pip. So whoa, wait a second. That looks like it's all good to go. Wait a second. Gmap. No problems this time. Voila, Gmap. Check that. Okay, so yeah, anybody that wants to do this using Gmap, I say, oh gee, that's okay. Sounds great. Yeah. But yeah, so you want to try to cobble those chunks or cells of code together and then create your own function, and then, you know, play with changing the number of clusters, maybe change a region, change an image. You can go into the Earth Engine catalog, pick a different year of Landsat. I just want to see some combinations of actually using a function in this for this purpose. So hopefully that's pretty straightforward and relatively simple. I felt like the cognitive load on the deep learning lab was pretty high. So you guys can use like something a little breezy. Now, yeah, any other comments or questions just about using Python and Google Earth Engine machine learning in this context? Yeah. There's also a bunch more resources here. So this is a overview of collaboratory features. This is just another Colab notebook, and you can, again, just file a copy it in your own drive, play with it. You could run it right here. When you run a Colab in a different place, you see, these are the table of contents that's a nice Colab innovation on top of the existing Jupyter notebook, I think. There's also documentation in here too, and what your environment is set at. So here's the documentation. So if I was over here and I'm like, wait, what is that? What is, I think I can, I wonder if it does other libraries too, but let's see. If I, only in that, no. Oh, code snippets. Sorry, that's something else. There is a help somewhere. I clearly am pretty new to this, but this has a nice overview of like getting into what is a Colab notebook and extra features. This Python installation, we went over this comparison of the syntax, but you can keep cruising down and see some more specifics about how to handle dates, how to create an export of images. It's a lot of stuff. This intro to Earth Engine Python API. So a lot of times when you'll bump into a resource, it'll be nicely formatted on a website, and there'll be this little button where you could run in Google Colab Lab. And this goes over a lot of different stuff for defining things and generating outputs. And unfortunately, when I clicked on this link, no way. Yeah, okay. Notebook not found. But it's really, see, it's going to the GitHub, and so it's just like a little off on that URL. So I added the direct link to the working URL, and you can run this and rock on and try stuff out there. This is the little Folium thing that I grabbed that little function from. And so the base maps and adding a layer. And then if you really want to explore more, these are these community tutorials that are pretty nice. Forest cover, loss, snow cover, Landsat, all kinds of good stuff. NDVI, time series. So, and you can click on any of these, like let's see. Let's say detecting changes in Sentinel-1. And then I can run in Google Colab, and then now you can run this stuff. And then there's Google Earth Engine resources for higher education. I wish I bumped into this earlier, but there's some more tutorials, and then you guys should know, have you been exposed to the Earth Engine apps? So it's pretty cool. you can actually build a whole interactive application. I showed some of those last time, and this is how to actually get going with building your own app. So it's not inside a Google Colab notebook. It looks like its own standalone website. And if you really want to find out all the what's the latest greatest, I actually went to this in 2018, the Geo for Good at Google headquarters, and it's really cool to see all the innovation. They had just started connecting things to TensorFlow with Earth Engine then, and you see just all this reporting out on how it's getting used to manage crises, look at environmental insights, climate change, and like they've got entire sessions on forest and nature. So it's an annual event. Any of you could actually go to this kind of thing. There's stuff on deep learning here. There's social inclusion. I know it's a topic of interest to many of you, talking about indigenous peoples, and animations and all kinds of stuff. The other obvious big player in the like spatial analytics world is Esri, and they have a lot of analytics there. It's not necessarily free, but you can get access with universities or large institutions. I like obviously open source because it doesn't matter. You can, as much as possible, do the work needed, regardless of your organization size or budget. But there's also, I asked Dawn Wright, she's the head researcher, lead scientist, I think is her title, at ESRI, to join us. She actually was my oceanography TA when I was an undergrad more than a couple decades ago at UCSB. And she's unable to join, but there was somebody else that was doing really cool work and applying machine learning at Esri that she recommended. So we'll see. I asked that person. Yeah, it's just good to know what else is out there. Okay, so maybe unless there's other questions or comments about this, I think I'll just maybe kind of come back to like what we've been covering a little bit, and then we'll dig into a little bit more of the deep learning. But we started with the second half. We started looking at like, what if you, as your input data type is like an image or maybe a sound or something that's really complicated, then deep learning is actually a great tool to try to tease apart these more complex patterns and classify things, especially. And you can apply some of those tools in satellite imagery, which unfortunately we didn't get to, but pointed to where it's possible. We just need some more resource figured out to turn on the paid services to do it. But you did see how you could apply the supervised and unsupervised techniques to satellite imagery. And so that's, understanding the footprint of things is I think a really important for environmental applications. And yeah, this is more of, even though we started in geographical space, we sampled points, and we really, for all of these techniques, we really were inputting a table of values, pretty much. I mean, Maxent automatically created that table for us, but we went from a table of inputs to then a whole set of images for the deep learning. We couldn't use these techniques to do the deep learning problems. And then we also applied not a table, but like whole rasters to do stuff en masse with the Google Earth Engine. So yeah. And then we really just have one more module on ethics and justice and bias on Wednesday. And then before we have our expert panel discussion and then group projects. So I'm so sorry, guys, that everything looked like it should have worked on the new folders I created for your group projects. But unfortunately, there's some extra little trick. So I've reached out to Brad at the Brand Compute team, and I'm sure he can fix it in a GIF. So I would kind of expect some point later today, maybe you already did it, that'll get updated. On Taylor, I have some admin access, but those permissions are, and actually it's good that you guys see this stuff. I think with maybe Fru or Julian, you guys kind of covered some basic file system understandings, yeah. Because yeah, this is when I was looking at this rainforest one. So, these are permissions saying that, okay, this is a directory, not a file. The dash would be a file. And then that's the owner permissions, the group permissions, and then everybody else permissions. So the owner has read, write, and execute. The group has read, write, execute. And then everybody else just has read, not write, and execute. And then this is the owner. This is the group. That's the size. And this is the last modified date stamp. Oh, this is the actual folder, rainforest. So it looked like, okay, yeah, that's there. I was looking at like what groups is Scout a member of, and Scout's a member of rainforest. So Scout should have right permissions to this folder. Dadgummit. But alas, this courses folder, just like the users folder, I think it's mounted from a separate system that also has Windows access. So if whatever permissions I'm used to using on a single machine don't apply in that case. So anyway, we'll get sorted. But yeah, I pointed to those commands before in that Kaggle group, and yeah. Yeah.
Project has to be a competition, or if they're able to different questions. So designing the visual one, I thought was good.
Which one is there was something you found? Yeah.
It's called Zoo Animal
Is it on Kaggle somewhere, or but is it just like a notebook?
Yeah, there's a bunch of notebooks and it looks just like a competition, but
But this is not a competition.
I don't think so.
Yeah, it's just a data set. Okay. Yeah, I would accept that. And I would encourage to try to do a competition, but I would accept just showing use of a data set. The reason I'd encourage an actual competition is really just for marketability for going onto the workforce. It's like, hey, this thing that everybody's doing, I've done it, and also just going through that process of submitting something where you're trying to take their test data set and identify the expected prediction, and then they actually check it and you get you show up on a leaderboard. I think it's kind of a cool experience to do that. But I would accept just running a data set. And I wonder if somewhere often the data sets are linked to the competitions. And I wonder if that might be visible somewhere. Yeah, because anybody can create a competition, and that usually is motivating. The UC Irvine actually has they do a lot of machine learning. They have an entire catalog of machine learning data sets So this is probably from there, but yeah, could. Yeah, but it looks like a good one. Yeah, I like it. Based on attributes, cool. Yeah, any other comments or questions about the Kaggle? Hopefully we'll get you guys group folders soon, or about the group project. Okay. Yeah, so it looks like everybody's signed up. Yeah, and yeah, and really this is just meant to be a shared learning experience, like you actually doing something, look, taking an existing notebook and then maybe making a few tweaks and then seeing if you can just submit the result and then sharing out on the different approaches that you've encountered while looking at these problems that people are chewing on. And then that's just a way that we can all learn from each other. Yeah.
See about logistics and our computing power with the scalar, are we going to be able to run a full data set in these competitions or?
Yeah, that's a great question. So I would say, just running a subset is totally fine. But trying a technique or two, I'd love to see. So it's not really about you getting to the top of the leaderboard. It's more about just trying out the techniques. So yeah, you can subset the data, similar to what we did with the iNaturalist data set. We took all 10,000 species and we just got 10. And so that's a totally fine way to approach it. Is that?
Yeah, I'm just thinking of kind of where we're gonna have trouble plots.
Some of these data sets can be quite massive. Like even the full iNaturalist data set, I think when I started to download it from my home, it said it was going to take 3 days. It was going to take up like a quarter of my my hard drive. So, but come to me, like we can talk about how to pare things down if you have anything that's too unwieldy. Yeah. Yeah.
Very good way to download the data directly.
Oh, you were asking about the Kaggle, right?
Yeah.
Yeah. So I'll try that out today. I haven't tried. Yeah, Kaggle. That looks cool.
Yeah, I got like an error when I was using it, and when I went Google the error, it seemed kind of like an unresolved issue. Threads that had that question and no answers to it.
A lot of times, like with iNaturalist, is it just to download and upload the data sets? Is that its main purpose, Kaggle?
Yeah. You like, data within a competition.
Yeah, I'll give it a shot and see how it works. Yeah, so Taylor is a Ubuntu Linux machine, and Apple actually made a decision that, I don't know, at least 5, maybe 10 years ago, to the underlying operating system is actually also Linux. So you might have similar issues if you try it on your laptop as Ubuntu. But we can try that. Yeah. A lot of times, like you'll notice that with the iNaturalist data set, that with the competition, these are often on Amazon, and this is something else that you'll like encounter, I think, increasingly. So if I look at this URL, it's so it's actually going to s3.amazonaws.com. and S3 is also just like probably the most common data storage for the web that is used. So there's also like, if it's just getting the data, like there was one of you actually bumped into like downloading the data. I turned off one of these R code chunks because it was just what I used internally, but it does serve as a bit of an example of how you might be on Taylor, have a URL to a data set, and then be able to download it. The problem with Kaggle is that usually you need to like log in to do stuff. So I'd imagine that the Kaggler is actually dealing with authentication on some level.
Yeah, I created an account and authenticated with a personal access to it.
Okay, great. Okay.
Yeah, it looks like there's like a command line interface tool.
Uh-huh.
Like that has its own like native API. But is there any chance that
Yeah, I'll try that. The Kaggler is the command line interface, right?
no, Kaggler is like a API wrapper for specific.
Oh, okay.
Kaggle is
Oh yeah, okay. So that I would expect to be a little bumpy, but the Kaggle client should be fairly solid. So yeah, let's do that. And then like a lot of the stuff under the hood is it's using curl is just the most common library to just go and download stuff, and it can actually do authentication. And what this is a GET request, but it can actually do a POST request. Anyway, this is the code that I use to download it and then unzip it at some point. Maybe that's not there anymore. But yeah, so I was just going to point out like this is in terminal. So I'm curl. I'm saying this is the output. This is where it goes, and then I'm untarring. Tarring is just like it's like putting everything into a folder pretty much, and then extracting this gzipped file. It's yeah, it looks, if you haven't seen this stuff, it's not intuitive, because programmers are lazy, so they use very, very sparse language to do stuff. But okay, I'll do the Kaggler. I'll try or the Kaggle, at least the command line. That should work. And yeah, feel free to share any other requests along those lines. And so maybe we could go in here and kind of talk about some of these issues that popped up. Let's see. I think the main one is just that it's really confusing when we're talking about how to set up the layers and understand the shapes and then what each of these functions kind of needs. So like how many steps and what's the batch size, and so what helps me understand is just the actual text and going through this and like looking up like steps per epoch. Just the big picture though, before like diving into that level of detail, actually let's go back to a simpler one. So we have this guy. Yeah, so see, do we do that one or maybe start even simpler? Yeah, let's go back a little bit further, and then I'll move up to that one. Let's see. I'm gonna start with. Look at this lab. And here I was saying, like just for the binary version, we look at this movie's binary classification. So we look at 3.4 in here. So classifying movies. This is like a really, really simpler version. And the main thing is this, is understanding like how the layers stack. And we want it, the input layer should be the same shape. So this first layer that is dense is the same shape as the input. So that there's 10,000 words in this input. And then the output is based on the fact that it's a binary classification. So that changes, in our case, we're actually using images. And so that example is with the images, we started with the dogs versus cat example, which is 5.2. So wow, it's not really fun now. Okay, so this is the tail end of this, where we're wanting to end with this softmax because we have up to 10. Yeah, this is the this is the one with the MNIST digits. So we want 10. We have up to 10 classes at the end. So that's why this is units 10. And it uses that softmax because it's that multi-class. And that's what this shape is 10 when we show the summary output. But the input is based on the size of that image. So it's 26 wide, 26 height, and then the 32 is the number of channels, I guess. Yeah. So then with the dogs and cats example, that's later here. These are color images. So now we have color images. And the input okay, so it's 100, the input shape in the code here is 150 wide, 150 height, and there's 3 channels, so red, green, and blue. So that first layer needs to match the shape of the inputs. And then the last layer has to match the shape of the labels that are going out. And then all the layers in between, that's like where the deep learning magic happens to allow more complex relationships to be formed. And the convolutional aspect is just having that window that's defined by 3 pixels by 3 pixels that can move around, and then to pull that and then send that to another set of layers. And then, yeah, you have to flatten it before you apply these last 2. This is new to me, so I'm kind of relying on the text. I hadn't done deep learning for this lab, but it's clearly where the things are going. So I really, yeah, seek your guys' input and you know, things that you learned in the process. Yeah. Yeah. So the flattening, that is, we talked initially about like array shape, and the flattening allows it to basically be in a shape that it can make a single prediction on. So that has to do with this. That's a dense layer, is when it's flattened, meaning that it's expecting just a vector of information. And then that's when we can actually make the predictions. And that is reflected here when here the shape goes from 7 by 7 by 28, 128. You just multiply these dimensions and you get 6272. So the flattening is just changing something from this 3D object where we're looking at things in that multi-dimensional space and just squashing it into a single one. And from that, we can actually then get to the size of the output label that we're trying to match. In this case, dogs or cats. So it's just a single label. Yeah.
I have a question regarding like sort of understanding the bigger picture, especially with the 10 species example. It was a little bit counterintuitive when I got better results for the standard neural net versus the convolutional neural net, even though like it has like more complex relationships built in. And I tried messing around to like add layers, and like sometimes like adding the layers actually made it like worse because of the performance. So I was wondering if that's like due to the fact that we don't have enough input data and it's like overfitting potentially, or if it's something else.
Yeah, that would be exactly my first guess too, is this, that because we do have so few data sets, or, you know, it's, what's crazy is that when we were first talking about like parsimony and overfitting, or we talked about multicollinearity with the being a problem when we're fitting like a generalized linear model and stuff. There's actually only maybe a dozen parameters, and in this case we've got a few images and, you know, like hundreds of thousands of parameters. So yeah, the overfitting can happen really quickly. And so if you don't, this deep learning approach, it's really good to understand the limits of these things. It's not magic. It's just, it's a way of setting up the problem so that given the right kind of input data, you can get like something that's actually useful. And in this case, with so few images, it would be impressive to do a good job, because this technique is really, this works when you have a lot of data to throw at it, and it really starts to fall apart when you don't have as good data. So even though the convolutional neural net is generally preferred for imagery, because we're adding more parameters, like you were noticing, in that process, and with those extra layers, and especially the dimensionality of those layers, then that we're getting that trade-off where the simpler model performs better than the more complex model. Yeah. But that might be different depending on the images that you have. So it's not universal. Yeah.
I'm so confused. I mean, I guess the input state size, but I'm confused about for this example, the difference between kernel size and tool size. It's like if you pull up in the code, why is the two or like what is tool size and kernel size?
Okay, so I think, yeah, so some of these figures, so there is a correspondence, I think, between 3.3 and 2.2, and I think that relates back to there are these images here. So it's like this stride, and and basically there's like, what happens is there's a moving window that gets applied throughout the image, right? So that's the kernel size. So it's looking at like, okay, what's going on within these 3x3 pixels? And then let's see if they have good wording about this, because it's a great question. The thing is that like there's edges that it reduces to a 2x2 basically. But how do we say this right? Kernel. And pool size. So the normal. Okay. This is the first take on it. They might not do a very good job at explaining the pool part.
Like, so the kernel size is 3 and 3 and the flow size is 2.
Here we go. Yeah. A big difference from convolutions that the max pooling is usually done with a 2x2 windows in stride 2 in order to downsample the feature maps by a factor of 2. On the other hand, convolution is typically done with a 3x3 window and no stride. Okay. Translating that into something. So I'll be honest, I don't rightly know. But I think I thought it had something to do with the fact that when you have a 3x3 window and you're looking at, you basically get a value assigned, you lose the periphery when you move that window as far as what things you can infer. And I thought that had something to do with then reducing it to 2x2, but I need to understand this a little bit better. I'm just borrowing from the existing. What's the difference? Yeah, so maybe we can Google this and I can get back to you. It's a really good question. I don't know the answer. Max pooling. So that. Okay, well, I'm gonna kick around. We'll have office hours today, and maybe we can take a deeper dive, and I can answer that question with a little bit more research and get back to you on Slack. Yeah, and guys, I'm really sorry that I haven't gotten the gradient. Just yeah, that's major downfall on my part. So I will yeah, get it to you. Yeah, but you guys are doing good effort, and yeah, I'm sorry. Yeah. Any other comments or questions? Cool. All right, I'll kick around and then also be around for office hours. And yeah, I'll try to help you out on the getting this lab in. So we'll still shoot for Wednesday for the lab, and I'll lurk on Slack more and try to respond to your other questions. So cool. Thanks.
Let's see.